All right. Well, I hope that everybody's having a good day. We're close to the end of the week, even closer to the end of the grading period. So the big item, remember, Monday is your second exam, and it's going to cover what? Okay, probability. So everything from the simple probability to conditional, okay, tree diagrams, lattice diagrams, things of that nature. You are allowed to use a 3x5 index card, so anything you would like to write on that to use during the exam, that is perfectly fine. In fact, I'd like to go ahead and have a quiz tomorrow over conditional probability. So a couple questions, we'll see how that turns out. That's coming up tomorrow. When did I say the assignment was due? Was it Friday? Okay, good, good, good. I think what we'll do is have the conditional probability quiz at the beginning and then just continue to talk about the problems that we're not able to make it to today. We finished up the lesson, but I want to go ahead and do a few more examples, again, just to get a little more practice, make sure you guys feel comfortable with it. But first is our focus activity. All right, Jacob, if you would turn off that light for me, please, sir. All right, so this one goes back into normal distribution, okay, which we haven't seen for a little while. So number one says, suppose X is normally distributed. Okay, remember that was our notation. What's the 37? What does that mean? That is the mean. There we go. So that's the mean. Now 7 squared, what's that? That's the standard deviation. Now, is it 7 or 7 squared? There you go, 7. You kind of ignore the squared because when you square standard deviation, you remember you get what we refer to as the covariance. Okay, so 7 is my standard deviation. Okay. All right, well, we want to use technology on these. Use technology to find the probability of X being greater than 40. Okay, so I'm going to come on over here. Let's see. So I'm on here. Let me go ahead and take off this. That was some trig problems a second ago. All right, so where do I go if I want to use normal distribution? Okay, so menu. Statistics. Oh, not stat tests. Distributions. There we go. We want distributions. Okay, what did you say, Stephanie? Normal PDF or CDF? CDF. There we go. Now, you want to go ahead and put in a lower bound and upper bound. On this particular problem, we wanted it greater than 40. So that is my lower boundary. So what do I put for an upper? Remember, that's just 99999 all the way across. Okay, so let me fill in a lot of 9s there. That should be enough. All right. And then my standard deviation was 37, or excuse me, my mean was 37, and my standard deviation was 7. Okay, so now I go ahead and click enter. And it looks like I have about 33.4%. Okay. All right, good. So about 33.4%. Does anybody want me to go ahead and kind of illustrate this with a Venn diagram?
I thought 40 was the maximum.
No, it's greater than 40, so 40 would be the minimum value, yes.
I'm reading it wrong.
Now I want to go in there, okay, use technology to find 37 less than or equal to X less than or equal to 40, so I'm going to go ahead and do the same thing. It was menu, statistics, distributions, normal CDF. Now I want it between 37 and 40, so it gave me both an upper and a lower boundary. The mean is still 37, and 7 was my standard deviation. All right, so what am I going to get on this one when I push it? Okay, so 16.6%. All right. That means between, in this case, the 37 and the 40, 16.6% of the data should fall in between those values. Okay, 16.6%. All right, good. In fact, talking about percents, you guys remember what's the percentage of the data that's within one standard deviation? It's in the 60s. Whoa, you all right? It's in the 60s. 60 what? Oh, a little higher. A little higher. 8. There we go, 68%. Now, what about within 2 standard deviations? This one's in the 90s. A little higher. A little higher. A little too high. 95%. And then within 3 standard deviations, how much of the data is below the curve? This is the only decimal. Ooh, a little higher. 99.7. There we go. So 68, 95, 99.7. Okay. Well, let's take a look at number 2. The weights of cabbages sold at a market are normally distributed with a mean of 1.6 kilograms and a standard deviation of 0.3 kilograms. So, for example, this one I'll go ahead and kind of sketch one. So here's my normally distributed curve. So it tells me that my mean is 1.6.
Teacher, sorry to interrupt, but I got a few quick announcements. 8th period baseball, report to Western Field during 8th period. Let's see. CA freshman football, report to Chapman 8th period. JV football, your game tonight is canceled.
Oh.
JV football players meet in the dining hall immediately after school. Thanks, guys.
Okay. All right, so let's see. So with a standard deviation of 0.3, we would add if we were above. So this one would be 1.9, and then we would continue 2.2. If I'm going below, then I would subtract, that would be 1.3. Well, in this case here, it says one wholesaler, and is it time for folks to take off? Okay. And what is this again? Swimming, diving. Okay. All right. Well, make a splash. You say parkour?
Yeah.
There you go.
Parkour.
There you go. Tell you what, Emmy, dab before you go off the diving board. Cool. All right. All right. Good luck, folks. Okay. Hey, take care. Hey.
Where's Laura?
Is anybody else?
I'm going.
Oh, Laura's coming. She's about to dive right in. No? Okay. Okay. All right, so anyway, let's see what A says here. One wholesaler buys the heaviest 10% of cabbages. What's the minimum weight cabbage he buys? Okay, so he only buys the heaviest 10%, right? Well, as you go through the normally distributed curve, the percentage increases based on the amount of data that you have here. So if I'm looking at a curve like this, if he only wants the heaviest 10% of cabbages, where would that be on this diagram? Yeah, it'd be on the right side, correct? So let's say somewhere right about here, there's some weight in kilograms, let's call K, where above that represents the heaviest 10% of what we're looking for. Okay? So we're going to go ahead and write this out. We want the probability of X. Now, how would I write this? Would it be greater than K or less than K? We want the heaviest 10%. So we want greater than K is equal to 0.1, or you can say 0.10. Okay. Now, does anybody remember what to do in this situation? Well, we are going to be using the inverse. That's true. We're given the percentage, and we want to work backwards to find an element in the data that would, in this case, represent the first value where the remaining data is 10%. But Radley, do you know what I'm referring to? Why? Why do we have to subtract this from 1? Okay. It's this right here. Remember, your calculator is only capable of taking less than. So if it's greater than, okay, so I'll do this in black. Let me write this up. So the probability of X being less than K would equal, he's absolutely right, we need to take 1 minus the percentage I'm given, so it's 0.9. There we go. Okay, so now we have all the information I need, and it's really easy to forget. Okay, so we have our mean, we have our standard deviation, and now we have the true percentage that we're looking for. So I'm going to come back over here. Let me document B out of this. So I go to menu. I'm going to follow the same line here. So statistics, distributions, but this time I want inverse normal because I already have the percentage. I'm working backwards. numbers. So the area we were provided was 0.9. We had, what was it, 1.6? 1.6, and then a standard deviation at 0.3. Okay. So as soon as I click OK, let's say about 1.98 kilograms. Okay, so that is the lowest weight that this vendor is willing to buy, 1.98 kilograms. Okay. Any questions on that? Is this coming back to you? A little bit? Okay. All right. Well, B, another buyer chooses cabbages with weights in the lower quartile. What's the heaviest cabbage this person buys? Okay, well, it's not giving me a particular value. It just says lower quartile. What's that mean? The bottom 1/4. So really, we want to look at, let me go ahead and do this in a different color. Okay, we want to look at some value. Let's go ahead and call this C this time because we're dealing with cabbages. So this right here would represent 25%. Okay. So I want all the cabbages that weigh less than whatever that lower quartile weight is. So if I were to write this out, I'd say P of X. Now, would this be less than or greater than? Less than. Okay, whatever the value C I'm looking for is equal to 0.25. Okay, so do I have to subtract on this one? No, you only have to subtract the percentage from 1 if X is greater than the value you're looking for. If it's less than, you take it exactly as is. Okay, so I'm going to do the same thing. Menu, statistics, distributions, inverse normal. So we're going to stick with the 0.25. We have 1.6 with a standard deviation of 0.3. And what is the weight? Okay, so I'd say 1.40 if we're going to do 3 sig figs. Okay, 1.40 kilograms. There we go. Cabbage. All right. Did anybody have all of that done before we started? Okay, Radley? All right, good. Did anybody have maybe just number 1 done? Okay, so more hands are going up on that one. All right, good. Are there any questions? Because as we go through, I definitely want to continue to spiral material that we haven't seen for a while back in, because it's definitely going to show up on those paper exams in May. Okay. All right, well, we have, this is number 6. You're only going to have 3 in this current set. You're going to get number 7 on Tuesday, and we'll turn those in on Wednesday. So it'll be one of our final grades to finish out this grading period. Okay, good. Let me go ahead and shut this down. And let's get back to probability. All right, just make sure I mentioned everything. I talked about the test and the index card. Tomorrow I said we're going to have ourselves a quiz on conditional probability, so I know you're all excited about that. Let's see here. Those other ones apply to pre-calculus. No morning tutorials next week. I've got morning duty in the dining hall, so I am super excited about that. That was sarcasm. Anyways, tutorials next week are going to be after school, so from 3:55 to 4:20 if you need anything. We have to test on Monday. I think that's it. Unless anybody has a question or anything before we get going. All right. Well, let's see. We finished up the lesson, but there are a few extra problems that I would like to take a look at. Okay, like this one right here. Okay, in a group of 100 students, 40 are taking algebra, 30 are taking biology, and 20 are taking both algebra and biology. If a student chosen at random is taking algebra, what's the probability that he or she is taking biology? Okay, so let's go ahead and set up everything. We've got 100 students here. Okay. 100 students in the universe, and we're talking about algebra and biology. So let's say A and B. So where should I start in the Venn diagram? Anything we know for sure? Okay, we know the number of students that are taking both. So this overlap right here, we got 20 students. But now how many are taking algebra? Okay, so only 20 are taking algebra, but 40 total. Okay, so I'm going to go ahead and put a 20 there. If there are 30 taking biology total, then only 10 are taking strictly biology. Okay, and not algebra. Okay, and am I missing anything? There you go. So this union right here of A and B only accounts for 50 of the students. So somewhere out there, I'm going to have to go ahead and place that 50. Okay. Now, the reason I wanted to go ahead and bring up this particular problem was this is conditional probability. Now, we normally recognize conditional probability because of what keyword? Given, but it depends on the way that it's stated. If a student chosen at random is taking algebra, what's the probability that he or she is taking biology? So our question, what's the probability that he or she is taking biology, but what do we already know about that student? That student is also taking algebra. Okay, that's my given portion. That's something that we know ahead of time. So I'm going to write it out using my notation. So the probability that he or she is taking biology, given that the student is taking algebra. Okay. Now I'm going to go ahead and apply the formula to the particular notation that I have right here. So this would be the probability of, what goes up top? Oh, not the union. The intersection. So the probability of taking both biology and algebra divided by the probability of biology or the probability of algebra. Algebra, whatever the given statement is, what you already know, that is what you divide by. Okay. All right. Well, this one's pretty straightforward. What is the intersection? Okay, 20. But now these individual parts, the numerator and the denominator separately, this is when you do it out of the entire sample space. So I know there's 20 students out of the 100 who take both. Now what's the probability of them taking algebra? 40 out of the 100. Now we could go ahead and reduce these, but I'm going to go ahead and wait for just a minute. What do you do when you divide by a fraction? You multiply by the reciprocal. So let me move this over here so I have a little more room. Okay, so this is going to equal 20 100ths times 100 40ths. Okay, so those 100s are out. So 20 40ths is 1/2. So there's a 1 in 2 or 50% probability that a student chosen at random is taking biology who also takes algebra. And remember, this is one thing that we keep talking about when it comes to conditional probability. Conditional probability is the event, the probability of an event, knowing that some other event has already occurred. So you're not looking at the entire sample space. So kind of think about this in those terms. The probability that a student is taking biology, knowing that a student is taking algebra. Well, there's 20 out of the 40. So that's exactly what we got when we set up the formula. The sample space got reduced from the 100 originally to the 40 because we were dividing for the probability of algebra. Okay. Questions? Are you ready for one on your own? Okay. Let's try this one. In a group of 100 students, 40 were randomly put into a Monday art class. Independent of that event, 30 students were randomly put in a Tuesday botany class. If a student chosen at random is in the art class, what is the probability that he or she is also in the botany class? Okay, so let me go ahead very quickly. That's not what I need. I don't know why I don't already have one set up, but I'll create one very quickly. There we go. Copy. There we go. Okay, because that looks way better than anything I'm going to draw. Now, I'm going to go ahead and give you 2 pointers as you go into this problem, 2 hints. This is also a conditional probability problem, okay, because of the way it's stated. What's the probability that he or she is in a botany class knowing what? Knowing the student is in the art class. Okay, so it is conditional probability, just like the previous one, but also, this is very important, independent of that event. Remember yesterday we brought up the idea of independent events, and we said that if they are physically independent, they are mathematically independent. Now, because we are told that these two events are independent, I can use this here. I know the probability of the intersection should equal the probability of A plus the probability of B. But you can only use that rule if you are certain they're independent. Okay, so with those two hints, I'm going to give you a little bit of time. And let's see if we can come up with the right answer. Okay. What I'm hoping to do is finish these problems up pretty quick so we can start looking at the homework. Has anybody finished the homework? Has anybody started the homework? Yay, okay. Anybody looking at the homework and thinking, wow, those are some really good problems? Not a single hand, really? Thank you, Jaylee. I appreciate that. This is an excellent opportunity. Go ahead and talk with your villain buddies. See if you're getting the same response. Okay. See if you're on the right track. Maybe you did something different, but you're still getting the same answer. That's very possible. Bless you. Oh, I'm sorry. I made a mistake here. That's times. That's times. That's my fault. My fault. My fault. I put the wrong operation on there. Sorry, sorry. Probability of A times the probability of B. That's my fault. Now, it looks like I made a mistake, but in actuality, it was a clever teaching technique to see if anybody was going to catch it. But fortunately, it got past you guys on that one. Let's see if we at least have the Venn diagram put together correctly. Can anybody tell me, we know that if we go ahead and say this is art, this is botany, we know there's 100 in the universe. Can anybody tell me the number of people in the intersection? Or let me rephrase, who thinks they have an answer for the number of people in the intersection, but they're just not sure? Cortland, what you got? Oh, it's very close. Not 10, Radley? 12. Okay, 12 is going to go here in the middle. Okay, so how did we get that? Well, let's see. Before we go ahead and go on with the conditional probability, let's just say the probability of choosing a botany student. Okay. Well, how many botany students were there? Okay, there were 30, right? So 30 out of 100, well, that's 0.3 if you just go ahead and reduce it. Okay, 3/10. All right, let's do the same thing for the probability of finding an art student. I know, that just seems kind of sketchy to me. Because art. Sketchy. I work really hard at these. Okay. It shows. How many art students do we have? 40. So that's 40 out of 100. Okay, 0.4. Now, aside from my little operational mistake, the probability of the intersection is equal to the probability of A times the probability of B if we know they're independent, and that's what we were told. So the probability of the intersection, I'll say art intersecting botany, would be 0.3 times 0.4, which is 0.12. Okay, but how many people are in the universe? 100, so 12% of 100 is 12. Okay, and now we just go ahead and start to work backwards off that. If I know that there's 40 people who take art, and I've already accounted for 12, how many are left? 28. So 28 would go there. How about the number of people who just take botany? 18. And what is that total? 28 plus 12 plus 18. So that accounts for 58. So that means I still have 42 people who don't take either botany or art. Okay. Is this making sense? Okay. Well, now from here, we really have everything we need to go ahead and answer the question. So if I wanted to take care of this right here, we would take the probability of art intersecting botany and divide it by the probability of what? Botany or art? Art. Okay. Well, we know that the intersection was what? Yeah, 0.12. Or you can go ahead and say, 12 if you want to. I'll just go ahead and go with the decimal. 0.12. The probability of finding an art student was 0.4. And what is 0.12 divided by 0.4? 0.3. So 0.3 or 30%. Was there anybody who got that answer? Stephanie, good. Okay. Oh, that's fine. That's fine. That's perfectly fine. Yeah, 3/10. All right. Good. Any questions? Were we close? If we didn't get it? Okay. Now we're going to skip the coin problem for just a minute. Okay. And you'll see why later in the period it will make sense. We're going to skip the coin problem. It will make sense. Hello, is this thing on? Okay. All right. Let me go ahead and kind of just show you a few problems to, again, make sure you feel comfortable knowing the difference between mutually exclusive and independent, because there is a huge difference. Okay. Mutually exclusive and non-mutually exclusive events. Let's say we have two truth sets. Remember, when they say truth set, they're just talking about the actual elements that belong to a particular set. So let's say A has 1 and 3, B has 2 and 4. So you have a die. Event A is the truth set of rolling a 1 or a 3. Event B is the truth set for rolling a 2 or a 4. So what's the probability of A? We have 2 options out of how many? 6. So 2 favorable out of the 6 total, so the probability is 1/3. Okay. Same thing for B. 2 different outcomes, 2 and 4, so 2 out of the 6, well, that's 1/3. So the probability of either A or B, the probability of the union, okay, well, that would just be 4/6, which is 2/3. But do you notice anything? What if I take their individual probabilities and add them up? What do I get? 2/3. See, I get the exact same probability. All right. This is the same as the probability of A plus the probability of B. We have this rule. This works because A and B are mutually exclusive. Remember, mutually exclusive means they do not have a what? There's no intersection. There's no favorable events that are going to occur in both. Okay, so this one is strictly 1 and 3. This one is 2 and 4. So mutually exclusive means there's no common elements. So if it's not mutually exclusive, that's got to mean what? That we do have some kind of overlap, that there are common elements. Okay, so let's say event A is the truth set for rolling a 2, 4, or 6. Event B is the truth set for rolling a 4, 5, or 6. This situation has an overlap. So let's say this is A, this is B. All right, so we have 2, 4, 6 and 4, 5, 6. What are the overlap? What's the overlap? The common elements. 4 and 6. So I'm going to put those in the middle. So A strictly has a 2, B strictly has a 5. Okay, what's the probability of rolling a die and getting a value from A? 1/2. There's 3 possibilities out of the 6 total, so that's 1/2, right? What about the probability of rolling a die and getting it 4, 5, or 6? 1/2. 3 out of 6 is equal to 1/2. Now, here's the thing. If I go ahead and take the probability of the union, probability of A plus probability of B, what does this give me? That gives me the whole, but that doesn't make sense. Okay. The issue is that due to the intersection, we're including the probability of a 4 or a 6 2 times, once with event A and once with event B. So we have to alter the formula to this if we realize they're not mutually exclusive. Okay. So if I go ahead and take the probability of each individually, I add them together, well, we got 1, but then I subtract the intersection. Well, what's the probability of rolling either a 4 or a 6? 2 out of 6. So 2/6 is 1/3, right? So what's 1 minus a third? 2/3. Okay. Now compare this to the probability of the union. What's the probability of rolling a 2, 4, 5, or 6? That's 4/6, which does become what? 2/3. See, now it matches up. Okay, so that's the key idea. When we're talking about mutually exclusive, that means they have no intersection, no common elements. If they are not mutually exclusive, there is an overlap, and you have to alter your formula just a little bit because of that. Okay. Questions? Well, alrighty. Let's do this. Independent and dependent events. Okay. So I have some pieces from a Scrabble game. 2 pieces have an A on them. 2 pieces have an E on them. If I put all 4 in a bag and randomly choose one of the tiles, I would have a 50% chance of getting an A, the same for E. So let's go ahead and create a tree diagram. So when I first choose, I'm either going to get an A or an E. Okay, so I have a 1 in 2 probability of that happening. Because remember, there's 2 A's and 2 E's, so 2 A's out of the 4 total. That's where I'm getting the 1/2 from. Okay. Now, if I were to go ahead and branch this off, I have another A and another E, another A, and another E. Now, right below here, I couldn't fit everything on the screen. Okay. Choice 1, I place the piece back in the bag, so this is replacement. The probabilities are not going to change. Okay, we were looking at this yesterday, I think, with red and black cubes, and we had some other examples like that. So if I were to go ahead and pull out an A, there's a 1 in 2 probability of that happening, but then I put the A back in the bag. So because I've replaced it, the probability of pulling another A is still 1 out of 2. And see, I haven't even drawn an E yet. What's its probability? 1 out of 2. Now remember, one thing I said about every time the branches diverge, that sum total should be what? Should be 1. It should be the whole. A half plus a half. Same thing over here. Half, half. Okay. So I believe it does ask for a question down here. What's the probability of getting 2 A's in a row? Take that branch and follow it through. Well, does anybody remember if I follow through one particular branch, what am I describing there? Starts with the I. That's the intersection. Now remember, if more than one branch has the outcome that I want, that's when I add those. We call that that's the union. Okay, so if I follow along this guy right here, okay, with replacement, what's the probability of pulling out 2 A's? 1/4. Along the same branch, you're going to multiply those probabilities. Okay. Questions? So the second choice is independent. It is not related to the previous one because you put that particular tile back. Now, start out with the same 4 pieces in a bag and randomly pick out one of the 4 letters. See the tree diagram. Okay, so let's create a tree diagram for this one. So here's A, here's E. So we start out the same. There's a 1 in 2 probability for each of these, but now I'm not going to replace the tile that I choose. Okay. So what would be the probability of choosing the second A? 1 in 3. There's only 1 A left out of 3 because remember I already took one of the tiles out. Now I haven't even chosen an E yet, but how many tiles are left? 3. So this is 2/3. And also that makes sense because what's 1/3 plus 2/3? Okay, 1. That's got to equal the whole again. All right, now this time if I go ahead and pull out an E, there's a 1 in 2 probability of that happening. But for A, it has 2/3 because I haven't chosen one yet. But for the E, there would only be a 1 in 3 probability. Is everybody okay? Anybody having a hard time? Okay. So what's the probability of getting 2 A's in a row if I don't place the tile back? 1 in 6. So it becomes much more difficult to do that if I don't replace the A. 1/2 times 1/3. There's your 1/6. Okay. All right, questions. All right. Now, I went ahead and skipped that previous problem because I think it's a good idea if you go ahead and try these, on your own where you have as much time as needed. Now, we have 2 problems left. If we absolutely just had to choose one, I would choose this one here. This is a really good problem. Okay. We got 3 boxes on a table. They're filled with white and black balls. You ultimately want to know what's the probability of getting a white ball at the end. So absolutely, I want you to try this one tonight. Let's see who can come in tomorrow with the correct answer. Okay. Now, if need be, we can go ahead and work this one together maybe tomorrow, but if you get the opportunity, try this one again. Okay, see if we can get it. All right. Questions so far? Now, I know I'm getting close to the end. We got about 6 or 7 minutes left, but maybe I can get a problem from the assignment done. Is there any one particular problem that people are looking at and thinking, I'm having a hard time with that? And maybe if we don't finish it today, remember, we're going to turn the homework at the end of the period tomorrow. So we will have some time in class to go over this, just like we did the previous one. Maybe not the entire thing. We'll kind of see. You guys told me you wanted to take a quiz, so that'll take up a little time. Why is everybody looking at me now? Okay. Ella's excited to take a quiz, right? See, she shook her head yes. Okay. And you have to believe me because there's no video here. It's just audio. Okay. All right, so which one? Two? Okay, let's look at the second problem. A coin is tossed 3 times. What's the probability of getting at least 2 heads, given that at least 1 head is obtained? Okay. Now again, there are several different ways you could approach this problem. Again, I'm a very visual person. I like to go ahead and have all of the different scenarios in front of me. So what I chose to do was a tree diagram. Okay, so this represents the first coin toss, so I'm either going to get a heads or a tails. Okay, I don't know, one day I might branch out and try something different, but for now I'm going to stick with this. You know what, I appreciate that. You know, maybe I wouldn't have as many jokes if I felt I was getting the laughter I deserve. Oh! Okay. Well, hopefully by the end, this problem won't stump anybody. Okay. So then we're going to branch off again for the second toss. So here's another heads, here's another tails, heads, tails. And then finally we have a third coin toss. Okay, so let's see if I can fit these together. Heads, tails, heads, tails, heads, tails, heads, tails. Ooh, there we go. And who knows, maybe at the end of the problem I can have changed some minds about this probability thing. Change your mind? It's a coin? Oh, yeah, okay. Now it makes sense. I used that before, but I'll stick with it. Okay. Okay, so is everybody okay that there are 8 total outcomes if we're ignoring order? Everybody's okay? All right, so what's the probability of getting at least 2 heads given that at least 1 head is obtained? So the probability of getting at least 2 heads, I'm just going to go ahead and put AL at least. I don't know, that's how I'm going to abbreviate it. 2 heads given that at least 1 head is obtained. At least 1 head is obtained. Okay. Well, what we want to go ahead and do is apply the formula to this, and then we'll go ahead and look at my diagram to see if it can help me out. So we're going to be looking for the probability of at least 2 heads, I'll just put 2H, given at least 1 head divided by what? Okay, the probability of at least 2 or 1 heads? 1. Remember, whatever's given, that's what we go ahead and divide by. So the probability of getting at least 1 head. Now, be careful about the wording here. At least, like if you're talking about at least 1 head, what does that refer to? What does that mean is okay? Yeah, that means as long as there's minimum 1 head, but it's still okay to get 2, it's still okay to get 3. All right. So, oh, I don't know why I did that in the middle, sorry. That's an intersection. So I'm looking for the intersection of getting at least 2 heads and at least 1 head. So which one should I really focus on in that particular statement? All the strands that have at least 1 or all the strands that have at least 2? At least 2. Because if you think about it, at least 1 encompasses the other. At least 2 is going to be a subgroup of the larger group. Because as long as you have at least 1, you're good to go, right? So I'm only looking for strands that have 2 or more heads. Well, how many does that apply to? Okay, 4. So I've got this one right here. I got this one right here. I got the third one, and I have a 4th one. Okay, so there's 4 out of how many? 4 out of 8. Divided by, now what's the probability of getting at least 1 head? There's 7 of those. Remember, there's only one way to not get a head at all. They're all 3 tails at the end. So this is 7 out of 8. Again, what do we do when we divide by a fraction? You multiply by the reciprocal. So can anybody tell me the probability for this number 2? It is 4/7. So we did get away with 1. Yay. Okay. All right. The one that I would say is probably the toughest one on there, or at least in my opinion, is number 3. Has anybody solved number 3? Or again, anybody think they got an answer for number 3, they're just not sure if it's right. If somebody were to tell me what they got right now, I would tell you if it's yes or no correct.
17.
It is not 17. No. It is not 18. Okay. All right. Well, thank you guys very much. We'll come on in tomorrow. We'll go ahead and do some more of these. We'll take our quiz, and that'll be the end of our week. Have a great day out there. Please don't.